All right, in this video, we are going to be wrapping up the last section of chapter 5 that we cover. We're going to do section 5.7, and we're going to do a brief kind of an introduction to an application to differential equations. So while this is not a DE class, there's no prior knowledge needed. But I do think it's important, since a lot of y'all will be taking DE as one of your classes in your curriculum. It's going to be interesting to see how multiple classes can kind of get you to the same point in solving certain problems. And so what I want to do is kind of want to show you just one of the more basic types of differential equations, how you would solve it maybe in a DE class, and then maybe make a comparison and show you how to solve a few problems using linear algebra instead. So first thing I want to do is I'm going to assume that a few of y'all have never taken a differential equation class, which is not required by any means. I do want to show you kind of a brief introduction of how we're going to relate what we're doing to what you'll learn in a DE class if you haven't had this yet. So if you were trying to solve a first order differential equation of the following form, dx dt equals a times x. Now, we call it a first order differential equation because there's a first derivative in the problem. This says the first derivative with respect to t of x has to equal a times x. So what you would do in a DE class of something like this is you would use algebra to get all of the variables of one kind on one side and then everything else on the other. So in this case, what I did was, if I tried to get all of the x terms on one side and everything else on the right. So from the first step to this step, I divided both sides by x, and then I ended up getting dx on top with x on the bottom, and I also multiplied both sides by dt to get the dt over next to the a. By doing that, what I can then do is that as long as you do the same thing to both sides, you can try to solve for x. So I would integrate both sides, and we know from Cal 2 that the integral of dx over x is the natural log of x, and then the integral of a times dt, since a is just a constant, would be at plus c. Now, going back to the original differential equation, you're trying to figure out what function of x makes this statement true. So to solve for x, I could then exponentiate both sides of the equation, and we know that e raised to the ln of x would just be x, and then you end up getting e to the at plus c. So then by algebra, I can rewrite that as e raised to the at times e to the c. And since e raised to some constant is just going to be another constant, we can then kind of rewrite e to the c as just its own constant, capital C. And so as you can see, putting this all together, we would say that x of t equals an arbitrary constant times e raised to the a times t. Now that seems very, very simple, and because it is. This is one of the more basic differential equations that you can solve. But what we're about to see, and I'm going to come back to this slide in just a second, how can we use this idea to maybe set us up for success by using linear algebra to solve maybe a more complicated problem? So let's look at this. Instead of just solving one DE at a time, which is what a DE class focuses majority on, I want to look at how we can tackle multiple differential equations at the same time. So for example, let's consider a system of first order differential equations of the following form, where you've got x1 prime of t equals a bunch of multiples of x of t, x2 prime of t equals a different multiple, and so on. So you're going to have a certain number of equations where you have a derivative function equals a combination of regular functions. In these equations, we let x1 through xn of t, those are just functions of t, and then all of the a subscripts can be any constant that you want them to be. Obviously, y'all all made it through Cal 2 to be in this class. All of the primes on the left represent the derivatives of these functions. So the crucial feature of this system is that it is a linear system, all right, similar to the one we just saw. It is linear in that, what if we were to rewrite this as a matrix differential equation? So I'm bringing in a DE, but I'm going to rewrite it as a matrix. So why don't we rewrite it as the vector x prime of t needs to equal the matrix A times the vector x of t. We can see that this is equivalent to all these equations at the same time if we notice that the following three things hold. If we let the vector x of t be all of your functions put as a vector, obviously let x prime be the derivative of all those functions inside your vector, and then we let the matrix A be the coefficient matrix of all the A subscripts that you see at the beginning. If we assume that those are written as vectors, we can now see that we can rewrite that system of first order differential equations as a linear matrix equation. Now, the question now becomes is, if we know we can rewrite it in a linear algebra form, or in a matrix form, I should probably say better, how would we go about solving this without having to use the DE techniques that you learn in that particular class? Well, here we go. Let's let lambda and vector v be an eigenpair of A. Now, as we've learned throughout chapter 5 here, lambda is going to be your eigenvalue and v is the respective eigenvector of that lambda. And once again, we're going to assume the basis when we're finding these vector v's. So remember, I know we've done it for the last few videos, that the only way for this to be true is if you find a lambda and a v that make A times the vector v equal lambda times the vector v. If that is the case, then for any arbitrary constant c, or I should probably say more specifically, for an arbitrary constant c, we can define the solution x of t, the vector x of t, to be c times the vector v times e raised to the lambda t, which you'll notice if I scroll just a little bit here, and actually I'm going to go to the first slide where it is. Remember, we found x of t to be c times e to the at. What we're going to end up doing is we're going to have to use the lambda and the v to write our solution. So we would let our lambda, which remember is your eigenvalue, be the constant of the power of t, or e, and then we're going to let the eigenvector be part of the arbitrary constant that's going to end up going in the front, because the c and the v will go together, and we will call that to combine the arbitrary constant. Now, one of the downfalls of this is you probably can already think, well, in most matrices, we found more than one eigenvalue, and that's true. And for each eigenvalue, you're going to have to find a basis of an eigenspace for each one. So that brings me to the two cases that we may run into. Let's assume that you have found all the eigenvalues of A, and we've listed them all out. We've learned how we can find corresponding linearly independent eigenvectors. Remember, that means you're finding the basis of each one, because we know that a basis will be linearly independent. Then one of the two cases that you see here will happen. If all of the lambdas that you find are real and distinct, which means they're all real numbers, so we're not going to do complex numbers in this video, and they need to be all different. If that's the case, then we can write our final solution for the vector of x of t to be c1 times the first vector times e to the first lambda times t plus ... and you'll just do a separate function vector for each one. So for however many lambdas you find, that's how many terms you're going to have in your final solution of the vector function. Now, we may not see this case today, but another case you need to be aware of is that what happens if two of your eigenvalues are the same? Well, that means that even if the eigenvalues are the same, you should still be able to find corresponding linearly independent eigenvectors that correspond to those two eigenvalues, or in this case, the one eigenvalue. When that happens, your solution is going to look very similar. You'll notice the only difference is when you get to the two terms where the lambda is equal. So you notice I still use lambda 1 and lambda 2 here for my notation. When you get to the second one that matches, you have to add an extra variable into your function. Otherwise, it's going to mess up when you start taking your derivatives to prove that it works. You only have to add this extra t if you have two lambdas that match, and it'll only go on one of the lambda equations. As long as they're all different, you never have to worry about adding an extra function in. So, using these two cases, this is how we're going to solve matrix differential equations of the linear variety. Now, we're not going to do a whole bunch of these because this is not a DE class, but I think it's important to see a couple of these just so you can kind of, as you go through your curriculum, you start learning that there is more than one way to do certain concepts depending on the application you're doing. So here's our first of two examples I would like to do. I want you to solve the following initial value problem. If I tell you that the derivative of vector x is equal to the matrix -4, -2, 3, 1 multiplied by the vector x of t, and I also tell you what the vector x of 0 is, it's the vector -2, 4, can you find the vector x that makes this statement true? Well, based on the terminology and the knowledge we've learned in the last 5 or 10 minutes in this video, you're going to have to find the eigenvalue eigenvector pair combos in order to set up your solution. So remember, the first thing you want to do is you want to find the eigenvalues of your matrix A. So we're going to find the determinant of A minus lambda I, and we're going to set that equal to 0. Now remember, from this whole chapter, for the A minus lambda I, you're assuming that you're subtracting lambda from the main diagonal. So when I find the determinant of that matrix A, it would end up being -4 minus lambda times 1 minus lambda minus a -6 is 0. So if I multiply this out, this is -4 plus 4 lambda, right, minus lambda plus lambda squared plus 6 is 0. And if I regroup this, it would be lambda squared, that's going to be plus 3 lambda plus 2 is 0. So that factors pretty nicely. It factors into lambda plus 2 times lambda plus 1. And so if you set both of these equal to 0, you get lambda equals -2. Oops, I went ahead and solved the second one without finishing saying what I was saying. And you solve lambda plus 1 equals 0, you'll get lambda equals -1. And while this is not your final answer, I'm going to box them in just for reference. Those are two distinct eigenvalues from your matrix. So thus, I'm not going to have to worry about the extra function here. To complete this, you need to find the eigenvector pair of each one. So for lambda equals -2, remember, when you're solving for an eigenvector, you need to plug your lambda into the A minus lambda I and set up the homogeneous matrix equation. So in this case, -4 minus a -2 would be -2, then -2, 3, and then 1 minus a -2 is 3, and I'll put my zeros on there. Pretty easy to see here that row 1 and row 2 are multiples of each other. So I know immediately that the most bottom row is going to go to all zeros. And while I'm here, I'm going to go ahead and take row 1 and multiply each entry by a -1/2 to make it 1, 1, 0. So this tells me that x1 plus x2 must be 0, with x2 being free, which means that x1 is going to equal -x2, with x2 being free. And if we write our entire eigenspace, that can be denoted by the vector x, which is x2 times -1, 1. All right. Now we only need the basis, so you can let x2 be whatever number you want to be. And I'm going to call this my first eigenvector basis. Those are nice whole numbers, so I'm just going to let x2 equal 1 in this case, so that my eigenvector becomes -1, 1. Repeat the process for your other lambda. So lambda equals -1. All right. So if lambda is -1 and I plug that into my a minus lambda I space, this will become -3, -2, 3, 2, 0, 0. Once again, your two rows are multiple, so the bottommost row goes to all zeros. And I'm going to take row 1 and this time multiply everything by a -1/3. So that will give me 1, 2/3, 0, which means that x1 plus 2/3 x2 must be 0. Thus, x1 must be -2/3 x2, which means, once again, x2 is still your free variable. I kind of just put it all together at one time there. So that means that my eigenspace is going to be the free variable x2, and we got the coefficient -2/3, 1. Now, for my second eigenvector, I am going to change this a little bit because I want these to be nicer numbers. So I'm going to let x2 equal 3, just that way that the fractions go away. So if I let x2 be 3 and multiply it through, I should get an eigenvector of -2, 3 in this case. All right, so that to be said, let's see where we're at right now. So if I come back down here to the bottom and write down my general solution, since there's two eigenvalues and two eigenvectors, my general form is going to be the vector x of t is going to be a constant 1 times your first eigenvector times e to the lambda 1t plus a different arbitrary constant times the second eigenvector times e to the lambda 2t. Well, if I plug in what I've already learned so far, we should get an unknown constant times the first vector, -1, 1, times e to the -2t, because that eigenvector went with my lambda equals -2, plus c2 times my second eigenvector, which I'm using -2, 3, times e to the -t, because it goes with lambda equals -1. Sorry, I had to add a new slide because I ran out of room here. So that would be your general solution here. But since the original problem gave me an initial condition, I'm able to now solve for what constants make this statement true. So what this initial condition tells me is that if I let t be 0, so I'm going to let this number right here go to 0, I can set up my equation. All right, so let's scroll down to the next slide. So if t is 0, that means the t here and the t here need to go to 0. So we would get x of 0 equals c1 times the first eigenvector. Now, this term right here is going to become e to the 0, and actually so is that one. And we know that e to the 0 is just going to be 1. So really, those kind of just go away. They don't make the whole thing go to 0, but they make each of those constants go to 1. So then you're going to have plus c2 times the eigenvector -2, 3. And this should equal whatever the initial condition was, which was -2, 4. If you notice, you have just found this to now be a vector equation, which we've been covering since the very beginning of chapter 1. To solve a vector equation for unknown constants, you have to set up an augmented matrix. So I would set up the matrix -1, 1, -2, 3, and we want this to equal -2, 4. All right, so row reduce at whatever rate you want to. Let's see. I'm just going to leave them where they're at right now. I'm going to take row 2 and I'm going to add row 1 because 1 plus -1 is 0. So -1, -2, -2. This should be 0. That should be 1. And then that should be 2. All right. I'm going to go ahead and get rid of the -2 on top. So I'm going to take row 1 and I'm going to add 2 row 2s to that. So 0, 1, 2 remains on the bottom. the top becomes -1, 0, and then -2 plus 4 is going to be 2. And then finally, scaling row 1 by a negative, because I need it to be reduced echelon form, you'll get 1, 0, -2, 0, 1, 2, and thus you have just found your constant 1 to be -2 and your constant 2 to be 2. You can now go back up to your x of t that you see at the very top of the screen, and I'm going to replace those arbitrary constants with what we just found. So the vector x of t is now going to be -2 times the vector -1, 1 times e to the -2t plus my second constant 2 times the next eigenvector times e to the -t. Now, what you will notice here is we're not done. We've got to put this together as one column vector in order for this to be our solution, as we saw earlier. So what we need to do is on this first vector, I'm going to take the -2 and the e at the same time and multiply those through. This should end up giving you a column vector of 2e to the -2t and then -2e to the -2t on the bottom. Likewise, I'm going to take this 2 and this e to the -t and multiply them through, and you should get a second vector of -4 e to the -t, 6 e to the -t. And since both of these are two-dimensional vectors, you can simply add them together and you will have your final solution. If you add the two top terms, they do not go together. This is just 2e to the -2t minus 4e to the -t. And on the bottom, that would be -2e to the -2t plus 6e to the -t. And this is the vector that makes our statement true. If you were to take this vector x of t and plug it back into the original problem and you multiplied it by the original matrix A, you would generate the first derivative of itself. And so that is the solution to our linear matrix differential equation. The first of two we're going to do. All right. So no real curveballs in this section. We're going to do another one exactly the same. It'll probably take me 2 slides to do it again. But just to have a second one in your notes and for the video, let's solve this linear matrix differential equation. So once again, I got to find the eigenvalue, eigenvector combos before I can start setting up my solution. So we are going to, once again, imagine that we have minus lambdas down the main diagonal. And over here on the left, we're going to take the determinant of that to solve for lambda. So this will be 2 minus lambda times -2 minus lambda minus a -3 equals 0. Multiplying that out, you'll get -4 minus 2 lambda plus 2 lambda plus 3. Oops, sorry, forgot the lambda squared. Plus lambda squared plus 3 is 0. This time, the lambdas cancel, and you're going to be left with lambda squared minus 1 is 0. All right. If we solve this, this will become lambda squared equals 1. And if you take the square root of both sides, you will get lambda equals positive and -1. So once again, that's two distinct eigenvalues, so we don't have to worry about any repetitions in our function. All right. We got to find the basis of the eigenspace for each of those. So let's begin with lambda equals -1. If I plug that into my matrix, that should be 3, 3, -1, -1 with 0, 0. So you're seeing a little trend here. Both rows are multiples. So the bottommost row goes to all zeros. Then I'm going to take row 1 and multiply that by a third to make it 1, 1, 0. Done these a bunch of times now. x1 plus x2 is going to equal 0. And so x1 is going to equal negative x2, with x2 being free. So my entire eigenspace x is defined as the free variable x2 times the vector negative 1, 1. And once again, those numbers aren't really that bad. So I'm going to let x2 be 1 here. So my first eigenvector will just be negative 1, 1. Let's repeat the process for lambda equals positive 1 now. So that will give me a matrix, or an augmented matrix of 1, 3, negative 1, negative 3, 0, 0. Once again, the bottommost row goes to all zeros, and the top row, we can just leave it as 1, 3, 0. So this time, x1 plus 3x2 is 0, which means x1 needs to equal negative 3x2, with x2 being our free variable. This eigenspace is defined as the vector x being the free variable x2 times the vector negative 3, 1. Once again, those numbers aren't too bad here, so I'm just going to leave those alone. I'm going to let x2 be 1 again, so that my eigenvector for lambda equals 1 will just be negative 3, 1. So now, using the same general form as the last problem, we have now concluded that our general solution for the vector x of t needs to be c1 times the vector negative 1, 1 times e to the negative t plus another unknown constant times my second eigenvector, negative 3, 1 times e to the 1t, or just e to the t. Let me go ahead and add my new slide and I'm going to need. Once again, if we let t equal 0, this should end up equaling 3, 2. So kind of the same idea as the last one. I'm going to let t be 0 in all these equations. Now you'll notice once again that when we let t be 0, both of those e's just become e to the 0, and thus will just become the constant 1. So you're left with vector x of 0 is c1 times negative 1, 1 plus c2 times negative 3, 1 needs to equal the vector from the beginning, which was 3, 2. As you can see, once again, this is a vector equation that we can solve by setting up an augmented matrix. So I'm going to do that. My augmented matrix will be negative 1, 1, negative 3, 1, 3, 2. So let's see. I'm going to take row 2 and add row 1. So the top remains the same. This will be 0, negative 2, 5. I'm going to go ahead and scale both rows here. So I'm going to scale row 1 by a negative, and I'm going to scale row 2 by a negative 1/2. So that will be 1, 3, negative 3, and then 0, 1, negative 5/2. So I need to get rid of that 3. So I'm going to take row 1, and I'm going to subtract 3 row 2's. So 0, 1, negative 5/2 on the bottom. And this will be 0. Well, no, it will not. It'll be 1, 0. And then you're going to have a little scratch work here for me because I don't have a calculator in front of me. This is negative 3 minus 3 times negative 5/2. So that's negative 3 plus 15/2. And let's see, that's going to be negative 6 over 2 plus 15/2, which would end up being 9/2. So we have just found that C1 is 9/2, C2 is negative 5/2. Take those two constants and let's plug them back into our general solution for x of t. So we now can see that the vector x of t needs to be 9/2 times the vector -1 times e to the negative t minus, because your constant's negative, your constant 2, so minus 5/2 times the vector -3 1 times e to the t. Just like the last one, I'm going to take the 9/2 and the e to the negative t and distribute that through. So that would be -9/2 e to the negative t and 9/2 e to the negative t minus, I'm going to take the 5/2 and the e to the t and multiply that through. So you should get -15/2 e to the t and then 5/2 e to the t. Those now go together as one vector, and we can write our final solution as the single column vector of the following. You'll have -9/2 e to the negative t plus 15/2 e to the positive t. And then your second entry on the vector would be 9/2 e to the negative t minus 5/2 e to the positive t. And this is the column vector that solves the original linear matrix differential equation. So while not a very long section, I did only work 2 problems here. I hope that this shows you kind of the very basics of how, even though this is a problem from a different class that we teach at Mississippi State, it does have factors that allow us to use linear algebra to solve and not always just use the methods you learned in a DE class. So that wraps up my videos for chapter 5 in this course. In the next video, we will be beginning the last chapter that I cover in this intro class. We're going to begin chapter 6.